Okay, this is your Chapter 16 video supplement, Renewable Energy, and as always, you should have read the chapter already and begun your work. So this is a supplement to that, and the first thing I want to talk about is solar cells, also known as photocells or photovoltaic materials. And some solar cells are made from semiconductors, and semiconductors, when you think about the periodic table, we've talked about it a little bit. So you've got metals. When you think about metals, you think of materials that are good conductors of electricity, good conductors of heat. Then you have nonmetals on the right side of the periodic table that are not particularly good conductors of electricity or heat. Well, semiconductors fall in your class of what we call metalloids or semi-metals. They're somewhat in between. They conduct electricity, but they're not quite as good as metals, but they're better than nonmetals. And the basis for all of our solar cells, for the most part, is silicon. Silicon is abundant. It's one of the most abundant elements in the Earth's crust. It's quartz, is silicon dioxide. All your sand, all of this, many of your minerals have a backbone of silicon, so it's very ubiquitous. But one of the keys is that we've talked about the electromagnetic spectrum. Silicon, sunlight has sufficient energy to excite electrons in the silicon atoms. Now, if you look at the periodic table, silicon is right below carbon. We've mentioned that carbon likes to form 4 bonds, right? And if you look at the periodic table and use the old notation, both silicon and carbon are in group 4. Okay, silicon right underneath carbon. And silicon then will have 4 valence electrons just like carbon. That's why it forms 4 bonds. Similar is what we're seeing here. Those number of single electrons is how many bonds they like to form. So silicon forms a nice crystalline structure. And when sunlight comes along, it has sufficient energy to excite these electrons. That's going to be key for getting electrons moving, because that's what electricity is, right? It's flowing and moving electrons. So there's a couple figures throughout your reading. I'll point out to you, 16.8 through 16.21 are all pretty good related to solar cells. So let's look a little bit at the chemistry now. This figure shows you 3 images, and on the left you have the pure silicon crystal. And then there you see the electrons I was talking about. This particular silicon in the middle, let's start with him. He's got 4 electrons, right? 2, 3, 4. The other ones that are surrounding it are being donated by each of these. And that's how you build the crystal. And this is our silicon crystal, with each silicon having 4 electrons. Okay, so what we're going to do is something called doping, and that means that all we're going to do is replace some of those silicon atoms, just a small number of it throughout the crystal, with something that has more electrons than silicon. And arsenic is a perfect example of that. If you look on the periodic table, arsenic has 5 valence electrons, has an extra one. So now you have this extra electron here in the silicon-doped crystal or semiconductor. And the last figure on the right has gallium instead of silicon. If you look at gallium on the periodic tables to the left of group 4, so it's in group 3, it only has 3 valence electrons, so it has a deficient electron, which means now you have more protons than you just have a deficient electron because you're donating 3 electrons instead of 4, so you have this what's called positive hole here. Okay, so this is going to be key. This charge imbalance is going to be key, so that when the sunlight strikes it and excites an electron, it now can be attracted towards this positive hole, and these electrons can move and flow, and this is what's going to give you your flow of electricity. And that's what's key to creating solar cells. That's a little bit of the chemistry that your textbook doesn't have, and I just wanted to share that with you. Now let's take a look at biomass chemistry. Now some of the chemistry here is beyond what I want to go into at this level of a course. Now we did introduce to you the idea of biomass and defined it. We talked about its chemical composition. And then I distinguished between biodiesel and ethanol. And we said that basically ethanol, for that case, is you're starting with basically sugars. And remember, sugars and are carbohydrates like starches. Starch. These are carbohydrates. Sugars are just simple carbohydrates. That's what you start with. You go through a fermentation process and you get ethanol, which is just an alcohol. Just an alcohol. We can use yeast for this. Okay? The difference with biodiesel, here you're going to start with oils or fats, if you will. A lot of this comes from the seeds, like sunflower seeds and stuff like that. So you're reacting these fats and oils, and ultimately you're going to get a biodiesel. So there's just different types of fuel, both starting with basically, existing products, natural products that are existing, as opposed to fossil fuels that were formed, millions of years ago. Now there is another option here. There are several options, but here's another common one, and I want to point out to you, is we can start out with any sort of organic material, and I'm just going to signify by this. This is like just a common notation used for just general organic material, because the ratio of one carbon to two hydrogen to one oxygen is fairly common in a lot of organic material. Well, if we take this through, we've talked about combustion reaction, which is basically, we've talked about photosynthesis and respiration. Combustion and respiration are basically the same thing as far as a balanced chemical reaction. Respiration doesn't involve heat, the combustion does, but the starting products and finishing products are the same. So this is a process that doesn't use oxygen. It's an anaerobic process. Bacteria will carry this out. So that means there's no oxygen here. The byproducts here are methane and CO2. Now you know from your previous work that we've done that methane is a fuel. It's the simplest hydrocarbon fuel. So what you can do is take organic materials, any sorts of organic, they could be waste materials, waste products, stuff like that. Take it through an anaerobic digestion, capture the methane, and use that. And remember, methane is also a heat trapping gas, a pretty substantial heat trapping gas. So you don't want to be letting this stuff out. But that is another way you can use biomass chemistry to get a fuel. The last thing I want to talk about that your book touches on but doesn't show the chemistry really, once again, that's what this class is designed to do. These videos are designed to supplement the chemistry that's missing from your textbook. So with hydrogen, we have something called fuel cells. And you'll hear a lot about the hydrogen economy. I'm not going to go into that so much as just really talk about fuel cells. Many reactions involve the transfer of electrons. In fact, that's the way your typical battery works. It's a chemical reaction in which electrons are being transferred. The only difference is you're forcing the electrons. Let's say you have A plus B going to C. What you're doing, you're going to separate A and B, and you're going to force the electrons to go out and to power something like a light bulb. I'm a terrible artist, so there's my light bulb, believe it or not. You're going to force the electrons to travel because they want to go from A to B, but you're going to force them to go through a wire, power your light bulb, and then go to B. That's the basic idea of how a battery works. So a fuel cell is going to do the same thing. The only difference is it's going to take hydrogen and oxygen are the reacting products, and the byproduct is simply water. Electrons get transferred here, okay, and they get transferred from the hydrogen to the oxygen. We're going to simply use those to power something. This is what we call, can be used in fuel cells. And this is what was used originally in the space shuttles. The first space shuttle was ever launched, not to power the shuttle and launch it. That's rocket fuel. That's different. I'm talking about powering instruments inside the actual shuttle, using it as an energy source. So you can get hydrogen from a lot of different places. You can get it actually from fossil fuels, convert your fossil fuels to hydrogen gas, and this is what people mean when they talk about the hydrogen economy. But there is no natural source of hydrogen that's ubiquitous. There's not a lot of hydrogen out there, so it's not really considered a fuel as much as a fuel carrier. We consider something as a fuel that's abundant that we can mine and then utilize. Hydrogen, that's not the case. You're going to have to get another fuel and convert it. And one thing you can do is take stuff like coal and convert it to hydrogen. That is the idea of clean coal technology. It's not particularly clean, but it is cleaner than just burning the coal. You're going to convert the coal and hydrocarbons to hydrogen-based fuels in a controlled environment. Makes it a little bit cleaner, a little bit easier to deal with. So, in summary from this chapter, what you're going to make sure you get out of your readings and filling out your worksheet and all of that is understand something about energy efficiency and waste, where our waste comes from and how to be more efficient. Solar energies, I talked about some of that here. Stuff I didn't talk about, hydropower, wind power, that's pretty much in geothermal. Pretty straightforward and covered thoroughly enough in your textbook. And then make sure you can distinguish between biodiesel and ethanol and biomass energy. And lastly, what exactly we mean when we say hydrogen energy and using hydrogen as a fuel. And that concludes your video.